Okay, in order to understand ion formation, we need a solid understanding of atoms and atomic structure. So just to review, I've drawn Bohr-Rutherford diagrams here in blue and Lewis symbols in green. Now, I have not included the neutrons in the nucleus, although you could have found that by subtracting the mass number minus the atomic number. The reason I didn't include the neutrons is that they do not impact the charge of the ion that is formed, and so I'm focusing in on the protons and electrons because those will affect the charge of the ion that is formed. So you will notice in all cases that the atomic number matches the number of protons, right? And that's how we identify the element that the atom is representing. So 1 proton, hydrogen. 2 protons, helium, right? 5 protons means this is an atom of boron, okay, and so on. Now, when you check out the electrons, there will always be an equal number of electrons to balance the number of protons when you are drawing a diagram of an atom, because atoms are always neutral. The protons must equal the electrons. So if there's 1 proton, as we determined by the atomic number, then there's 1 electron. If there's 3 protons, as determined by the atomic number, then there needs to be 3 electrons. 1, 2, 3. You'll notice not all 3 go in the first shell, and that's because the first shell is full with 2 electrons, so we need to move on to the second shell. 11 protons for sodium, therefore 11 electrons in total, splitting them up 2, 8, 1. And you'll see that that pattern exists right throughout all of these structures. Going over here to argon, atomic number 18, so 18 protons, therefore we need 18 electrons. Fill the first shell with 2, fill the second shell with 8, and we fill the third shell with 8, and for a total of 18 electrons. And that's why these atoms are neutral, because the protons and electrons are equal. Now, only the noble gases are stable. Only the noble gases are unreactive. We would want a birthday balloon to have helium in it, not hydrogen. So noble gases are stable. They're very unreactive. And another name for that is inert. And so we can see through their electronic structure that the valence shell, the outermost electrons, the outermost shell is full. Here we have 8 electrons in the third shell, 8 electrons in the second shell, 2 electrons which fill the first shell. None of the other atoms are stable. None of the other atoms have a full valence shell. And so atoms are always neutral, and in most cases they are not stable. The noble gases are stable. All right, something else to notice would be the patterns, right, in the electron arrangement. So you'll notice that the group number, being this being group 1, corresponds to the number of valence electrons. 1 valence electron for all these atoms in group 1. 2 valence electrons for all of these atoms in group 2. Now I've omitted the transition metals. Bohr's model is not useful for explaining the chemistry of those, and we need the quantum model of the atom for that. However, that's for another course. So moving on to group 13, we have 3 valence electrons. 1, 2, 3 in the second shell. Here for aluminum, we have 3 valence electrons, again in group 13. So it's the second digit, the 3, that tells us the number of valence electrons. For group 14, 4 valence electrons. Group 15, 5 valence electrons. And you'll see that pattern holding all the way throughout, except in the case of helium, where group 18 we're expecting 8 valence electrons, which is true for neon and argon and the rest of them. However, helium doesn't even have 8 electrons to start. With only 2 electrons in its shell, it has 2 valence electrons. However, helium is wisely positioned over in group 18 for its stability. Again, the common feature that the valence shell is full. So we can see that the group number tells us the number of valence electrons. The period number, right? So hydrogen and helium are the only period 1 elements. Notice that they have 1 shell or 1 energy level. Period 2, we have 2 shells all the way across. Period 3, 3 shells all the way across. And period 4, we see 4 shells. So the period number will tell us the number of shells, or orbit, or energy level. You can use those terms interchangeably. Okay, now a faster way to represent these structures is to use Lewis symbols. When we draw a Lewis symbol, we use the element symbol, and this element symbol represents the nucleus as well as any inner electrons. The dots represent the outer electrons. And so here I've given you a little description here of the Lewis symbol. Lewis symbols are very helpful because they focus us in on the valence electrons, and the valence electrons are the electrons involved in bonding, and therefore they'll be very useful for us as we start to look at how atoms form chemical bonds. So for now, we're just drawing Lewis symbols of the atoms in each of these boxes. So you'll be using the group number to tell you the number of valence electrons, and that will tell you how many dots to write beside the symbol. So here we'll see magnesium with 2 dots. Now you could put 1 on one side and 1 on the other, 1 on the top, 1 on the bottom. It really is, doesn't have to be one particular way. When we are drawing Lewis symbols of atoms on their own, we typically don't put more than 3 on the top, bottom, left, or right, so just be sure not to stack them any more than 2. All right, and it's okay to pair them up. So you'll notice chlorine over here in group 17, 7 valence electrons, and argon with 8 valence electrons. All right, so this is a review of our foundation here to now study how ions are formed. So when we understand atoms and the fact that they're not stable and why they're not stable, then we'll be able to make them stable. Okay, so now we'll look at ion formation. So first thing I'd like you to notice is that I have put blanks in a few of these element boxes here. You'll notice the noble gases. Noble gases are already stable, and so they don't need to form ions. Silicon and carbon, for that matter, so I'll draw a blank here in carbon, typically become stable by sharing electrons, not by losing or gaining electrons. And it's the losing or gaining of electrons that form ions. So since we are focused in on this in our diagrams here on ions, we're going to omit carbon and silicon. Boron and beryllium also very commonly share electrons to become stable. And so you'll see what I've written here at the bottom, the octet rule, that atoms either share, lose, or gain electrons to achieve a full valence shell. If atoms that are not stable share electrons to become stable, that forms a covalent bond. If atoms lose or gain electrons, then to become stable, then they are forming ions, and it's the attraction between the ions that forms ionic bonds. So we're going to focus in on the lose or gain of electrons to achieve a full valence shell. All right, so we're going to start with lithium here. Okay, so I'm going to zoom in on the lithium box, and you can look back to see, how that worked for your atoms, but your atom of lithium, but I'm going to draw that again here. So we had a Lewis symbol for lithium that had 1 dot representing the 1 valence electron, and we had our Bohr-Rutherford diagram without the neutrons, right, that showed 3 electrons. So right now I've just redrawn what's on the atom page. So let's think about stability. If the outer shell is full, then this particle is stable. So there are 2 shells. The second shell has only 1 electron, so it's not stable because it's not full. Therefore, this atom is going to lose or gain electrons to become stable. So ask yourself, is it closer to empty or closer to full? There's 1 electron here. The second shell will be full with 8. It will be empty with 0. So if we only have 1 here, it's definitely closer to empty. So what happens then is that this atom of lithium will lose that 1 electron, which essentially empties that second shell. And so by doing that, we have now formed an ion, which is why I need to put square brackets. I'm going to be writing a charge outside the square brackets. Compare the number of protons to the number of electrons. We have 3 protons and 2 electrons. In fact, it might be easier if you need a visual of that. I mean, I've drawn the electrons in the diagram there, but if you think of this as being like 3 positive particles, right, and only 2 negative particles, do you see how 2 protons and 2 electrons cancel each other in terms of charge, and that leaves us with a positive 1 charge left over. Now in chemistry, if the charge is a 1, right, whether it's positive 1 or negative 1, we don't write the 1, we just put the symbol, the sign of it. So I'll represent positive 1 with a positive symbol. So what I've drawn right here is the Bohr-Rutherford diagram of a lithium ion. Okay, and I'll just be clear to name this a lithium ion. Notice the name of the metal doesn't change. Looking at the Lewis diagram up here, the Lewis symbol, I can see the 1 valence electron there and now remove that 1 electron in order to make that particle stable. And in doing so, I will put brackets and the charge up front. So there's outside. So there's a lithium ion. Okay, so we see that lithium, right, as a metal, loses an electron there to become stable. You'll need to think about the other particles, right, to think about what they'll do to become stable. And the key is always thinking of the shell, the valence shell, being closer to empty or closer to full. Let's have a look at nitrogen. So originally, on your atom side, you have nitrogen having 7 electrons. 2 are in the first shell, and there are 5 electrons in the second shell. When we did the Lewis symbol, we showed the 5 valence electrons. Okay, so those are the atoms that I've drawn. Are they stable? No, the valence shell is not full. Okay, that means it's going to lose or gain electrons to become stable. Well, is that outer shell closer to empty or closer to full? We have 1, 2, 3, 4, 5. This shell would be full with 8 electrons. So we have 5. Is that closer to 8 or closer to 0? Hopefully you agree with me that it's closer to 8. And so I'm just going to use a different color just so that that stands out for you, right? To show you how we can complete the octet of this atom, this particle. And by doing that, now that we have 8 electrons in the outer shell, we've now changed the number of electrons. Originally we had 7 protons, right? And originally we had 7 electrons, but now we've gained 3 more, so now there's 10 electrons. So think about the positive particles, right? We originally had 7, and we still have 7. We never changed the electrons, never changed the protons. And now 1, 2, 3, 4, 5, 6, 7, right? 8, I'm running out of room here, 9, 10. So these positives and negatives will cancel each other 1 for 1, if you need this visual to help you, right? And you'll see that we have 3 negative charges left over. And that's why the charge of the nitride ion is -3. Now, you could write your charge as either 3 negative or -3. Okay, that's fine to do it either way. So why is the charge -3 or 3 negative? Because there are 3 more electrons, right, compared to the protons. So it's true that a gain of electrons will always form a negative ion, and that a loss of electrons will always form a positive ion. Okay, so you've seen an example now of how a lithium atom forms a positive ion and how a nitrogen atom forms a negative ion. And what we've done now is create particles that are charged because the protons and electrons are not equal. However, they are stable. They're stable because their outer shell is full. For nitrogen, we filled up that second shell. For lithium, we emptied it, which means that the shell below is now the valence shell, and that shell is full. And so these ions are stable. So what I'm asking you to do then is to complete the diagrams, both Bohr-Rutherford and Lewis, for the ions of the elements that I did not put a line through. Okay, so you have a few to do there. When you're finished, have a look at all of the metals on this side, right? Thinking that the staircase, right, runs here. The staircase that separates the metals from the non-metals, right? Kind of goes like this. Okay, so have a look through, right, at all of these metals and fill in the blanks here. So do metals lose or gain electrons to form, and what is the charge of those ions? And I've given you the term there also, as well as this statement. Non-metals either lose or gain to form anions, positive or negative ions. What do the non-metals tend to form? Okay, and one last piece to this. I did name the metal ion, the lithium ion, and I just used the name of the element, lithium. And that's what we do for the metals. So the sodium ion, the magnesium ion, the aluminum ion, and so on. So anything to the left of the staircase, we use the name of the element as the name of the ion. The negative ions, however, this is where you will see a change in the ending. And you've already named these ions when you've done your ionic compound nomenclature, but I'd just like to point out that the N3 negative or N negative 3 ion, right, is the nitride ion. Okay, so that's the name for that. Similarly, when you form the oxygen ion, it's actually called the oxide ion, as well as the fluoride ion. So just to be clear, so you can see how this links to the nomenclature that you've learned in grade 10 and will continue to use, right? These are the names of these ions: phosphide ion, sulfide ion, chloride ion. And so the nonmetals, we always see this IDE ending. Okay, so I'm asking for you to complete the ion diagrams, both Bohr, Rutherford, and Lewis, for each of the boxes that don't have a line through them. All right, now I'd like you to do that, and I will myself complete it on this table so that you can check back with the end of the video here to correct your answers. So definitely pause the video now, please, so that you can do that work, right? And just come back to the very end of the video to check your answers, okay? Take note of the charges that you find each element forming within a group, all right? And you can indicate those charges at the tops of the groups to help yourself later with nomenclature. Okay, so here you go. You can zoom in and you will see all of the Bohr-Rutherford diagrams of the ions with the Lewis diagrams, as well as the names of the ions. I have filled in the blanks here, noticing that all the metals lose electrons to form positive ions, which we call cations. Group 1 forms positive 1 ions, group 2 form positive 2 ions, group 13 forms positive 3 ions. And then we see the anions, the nonmetals, gaining electrons to form negative ions. So we have -3 in group 15, -2, -1. the noble gases do not form ions. And I'll just make one comment about the hydride ion. It's true that hydrogen has an option to become empty, which is the hydrogen ion there, or fill up that first shell with a gain of 1 electron. That would give it a -1 charge, and we change the ending then, just like we did for these other negative ions, to IDE. 99% of the time, the hydrogen atom is going to form the hydrogen ion with a +1 charge. Okay, so I did show you this because I'm sure that question came up in your mind as you were thinking about hydrogen, but you can very commonly form the hydrogen ion, +1. Okay, that'll be the one we use.